Well, hello there. Got quite a bit of an update on the MIDI MEDUSA project, the MIDI 16-channel splitter. Here's what I got so far. I continued working on a design of basically the potentiometer, the notched potentiometer, which is effectively my attempt at taking a regular potentiometer and then giving it detents so that it has fixed positions rather than continuous motion. And the idea is that it would allow me to use a single potentiometer in order to make program selections. So what we have here is just such mechanism. Oh man, that that is so satisfying. There we go. I feel like Marty McFly about to blow up an amplifier. The principle of operation is still the same. We have a base with a bunch of notched detents. These create kind of like a little catch well. We have a knob. Now this was just a size fit print. There is a little hole on the side of the future revisions of this where I deposited a spring and a little ball, little tiny ball bearing, and that ball bearing presses up against one of these grooves and causes the knob to snap to one of the angles. And I gotta say, this feels pretty gosh darn satisfying. Now, as good as this system appears to be, I had actually spotted a bit of a problem. So we've got a 10K potentiometer sitting on the back side of this, and why don't we observe some numbers so we get in return for this. So here I have Mount River Studio up and running, which is the programming environment for these tiny little CH32 series chips. I have some values that are being watched, and we're just going to give it a second to launch the debugger. Alright, so we're looking at the knob value at the moment, which is in this current position. It's currently being over-reported. I'm just going to refresh. We're going to actually need to place a breakpoint. Oh, there we go. That has been tripped. Let's put a breakpoint on... Yeah, sure, there we go, that's fine. So right now the knob value is being reported as 474. 474, and this is being somewhere around here. Okay, that's 474. So if I relaunch and let it break again, 474 still, 473, 475. A little bit of meandering is understandable. I think a bit of a filtering circuit is kind of required, but let's see what starts happening when we move the knob closer to one of the extremes. So I'm gonna do the following. I'm gonna move it over and then let the camera focus. Okay, 407, not bad. And then if I refresh, whoops, 407. Told it to restart instead of refresh. 406, 406, not bad. Okay, so relatively stable. Okay, let's go down to here, or here. What do we got here? 115, okay. 123, 115, 115, 116, 115. Okay, let's go down to 16. So that's the second last position. 0. Oh. 0, 0, 0. But as you can see, there's still a whole other position that is also reporting 0. So it seems like, let's go to 15. Yeah, 48. So this one it can recognize because we see a change, and we go to 16 and it goes to 0. So anything after channel 16, which is supposed to be the omni-channel selection, does not get recognized, which tells me that that this potentiometer has a dead zone somewhere at the end, either, yeah, it looks like the rightmost position. If we go down to, say, channel 1, like this, and refresh, 1023, which is the maximum value for the 10-bit ADC of the chip that is reading the value of the potentiometer. Let's go down to 2. That would be 1011. So on this most side, these last two positions are perfectly distinguishable. On this side, channel 16 and omni-channel would not be distinguishable. Now, that potentiometer did come from some failed experiment. I think this was some sort of a test at an impromptu audio mixer. It's the only 10K potentiometer I had lying around that is in this particular form factor, and I like this form factor because it's very beefy. It seems like something that would come in like a nice receiver, right? Nice amplifier. So that's why I wanted to use it. It's got some oomph to it when you move it around. This one, of course, is a 1 mega ohm potentiometer. This was way too heavy to be detectable by the chip. So equivalent to this, same form factor, but 10K is what is currently being driven here. And yeah, it appears like there's a dead zone, so when it reaches these two positions, they both get reported as the same value. So this had prompted me to try to redesign the detents, the notches, which is what I've been doing today. See, this particular version of the knob currently has a nice, positive 50, negative 50 degrees travel, because this would be around 90, and right here will be 45. So you can see that it can go way past 45, but of course this value doesn't get detected. So I had rearranged a new version of the notches that go between, let's say this is 90 degrees, so it's about like 30, 45-ish, 30 degrees. So 30 degrees up until whatever the equivalent of 30 degrees is on this side, and that's going to be the range. So we're just going to drop the entire range of values from here to here just to avoid that very side extension at the very extreme sides of the potentiometer values. So here you can see I've been modeling this in Blender. I know you can technically use, or you technically should be using CAD for this, but you use whatever you got handy at the moment. So we've got plus I don't think this computer is going to be able to handle any CAD software whatsoever. So we've got first of all, I made this little stopper right here. This whole section here is quite literally meant to prevent the knob from going there, even though technically the potentiometer could be spawned there. So there's a hard stop right here. This is the cylindrical port is for the spring and the ball, and of course all these notches are for the individual selections, detents. Each one of these dips is a separate selection. Everything else is pretty much the same. I decided to relocate the location of the detent, or the location of this ball bearing chamber, to line up perfectly with the side of the knob, so that I know that whatever the let's say the arrow over here, if there was an arrow, whatever that's pointing, that's where the ball bearing and the spring are located as well. So that makes it mighty easier to align all the detents. So I'll toss it into the 3D printer once it's finishes printing some little bobbins for magnet wire I'm printing, and that is going to be my next test. But this isn't even the extent of the achievements on this. I got more to show. So knob and potentiometer aside, I placed the little developer chip onto this nice little breadboard just so that it's a little bit easier to work with. I placed a decoupling capacitor. That thing looks a lot beefier than what it's supposed to do, but I suppose that shouldn't be too much of a problem. We've got a little debug light that I finally desoldered from the Frankenstein position that it was at, which is soldered directly to the pins, and this is much easier to work with. But the most important thing that I figured out is a bit of a problem that has been driving me nuts, and it's the fact that every time I push code onto this chip, it would stop being flashable. Like I wouldn't be able to push code onto it until I go through this whole cock and dance routine of setting the power down right state, unlocking the write protection on it. It's just all of this ridiculous stuff, which means that I could upload code at the speed of about like once per every 15 seconds. That wasn't very convenient. And I realized that the reason why this was an issue, or the cause of this little issue, is because when I was configuring the serial port on this device, because, you know, obviously we're going to be reading serial information, serial data from the MIDI port of music hardware. When I had set up the serial port on this chip, the transmit chip was allocated to one of these free pins, which is pin number 1 in this case, or that's a receive actually. That's one of the few pins that is capable of receiving serial data. But the transmit I had actually set to pin number 8. And if you guys know what this chip is, pin number 8 is SWIO pin, which is the programming pin. As you can see, it is the white wire going directly into this guy. There it is. And the white wire right there. SWIO. So this was actually the pin, specifically the pin, that is used to program this chip. Now, I'm not entirely sure how exactly going through the routine of configurations allowed me to reflash it. Maybe whatever I was doing caused the chip to basically just power down, at which point the serial data transfer would cease to operate, and then the program pin was free to, well, program. But here's the routine I had to go through in case you were wondering. So in Mount River, in order to upload a piece of code, you use this little download button. I had to go to the configuration, query the programmer. I would have to set the erase code flash to power off. When I click apply, oh, as you can see, it's getting stuck right now because I finagled with the communications command error. I need to unplug and replug the programmer because I twisted it when I was showing it the wiring on the back of it. Let's try that again. Query, apply. There we go. So set erase code flash success, and then I am able to disable code protect. So code protect disabled, apply and close, and then I can press download. And fascinating. Alright, if you ever experience that, I for some reason have to rebuild the project, even though I just did it a few minutes ago. So after I did project, build project, I can do download, and that's it. And now it's downloaded according to the nice little green reply. So after this, anytime I would hit download the code onto the chip, it would fail. And I would have to go through the same exact process. Query, power off, apply, write code protect, apply, and then upload. So if you ever experience something like this, my well, learned wisdom of this particular issue dictates that you've likely set one of the right pins, or the right pin, as WIO pin, which is pin 8, to also run some sort of a peripheral which is interfering with the programming. Thankfully, when you do that, it doesn't just immediately forever brick your ability to program that chip. So thankfully there was a way to back out of it, and everything was hunky-dory from that on. I just moved the functionality of the transmit pin onto pin number, what is it? I think it's pin number 5 down here, which was unoccupied. As a matter of fact, I think it's this pin right here. But alas, there is more progress still. What you see here is a little MIDI input circuit that is based on the 4C or 4N28 optocoupler, which is this little white chip right here. And what this does is optically isolate this circuit, which is the MIDI input circuit. So this is coming from your MIDI source, like a MIDI keyboard, for example, and it transfers all the data while optically isolating it from the circuit of this chip, which means that they are not electrically connected together. If something happens on this side, let's say like a high voltage spike, that high voltage spike is going to be stopped by this isolator, which is perfect. This is the usual recommended way of handling MIDI input circuits. And in order to test this, I'm using this Arturia keystep. Nice little keyboard, very sturdily made, and I use it for development purposes because it's a very, very nice and very reliable and very versatile keyboard. Like, for example, you can see here that it allows me to select a MIDI channel of my choice. So if I were to press any keys, you can see there's a little light on the MIDI controller that lights up whenever I press any keys. And here's the cool thing. I've already programmed that little chip, that little CH32 chip, to do MIDI channel filtering, which means if I were to press shift on this key step controller and press this key, which has number 2 under it, this switches the keyboard to use MIDI channel 2. And as you can see when I press the button, the keys, we no longer have that light lighting up, which means it is filtering out channels. I can switch it to channel 6, nothing. Switch it to channel 9, nothing. When I go back to channel 1, we see the light again. So it's already doing that job. Now, I've looked at the MIDI breakout, or the table of MIDI messages, so to speak, the MIDI protocol. There's only really a small number of messages that are tied to a particular channel. A lot of the messages seem to be omni messages, like what's a play, stop. There's a couple of like system program messages that seem to be transferred everywhere. So I have to really do some extensive testing to make sure that those messages are propagated to all of the outputs, but the general principle of operation is it accepts MIDI messages of all channels and then filters out only the ones that are set by this big knob. So in reality, all that remains to be done is to make it so that this knob, once I get the next revision of the detents in here, this knob allows you to choose which channel it is going to be filtering the MIDI messages for. And then when you send, let's say, if you have a MIDI interface that has one of those maybe like 4x4 ports, it has 4 physical ports, and of course each port can carry up to 16 channels. You'll have a separate device, the MIDI Medusa, which has 16 of these knobs, and it will break out the one port with 16 channels into 16 ports, one channel. So hopefully we are within the sight of a functional prototype. All that's really left to do is revise this design so that the last 2 channels are actually detected, and program it so that the position of the knob translates to a channel choice. And realistically, after that is just taking this whole thing and repeating it 16 times. And that's it. It's 16 independent processors running the same exact code. They're all just going to be flashed with the same exact program. And I think that is better than my initial consideration, which would have been to have some sort of one single beefy controller with 16 serial ports, which I've looked into that. It's not looking either cheap or really software-wise feasible. Considering how cheap these guys are, they're like what, 10 cents, 15 cents for one. I bought like a pack of 500 of them for what, 20 bucks or something. Yeah, these things are really, really cheap. So having one single chip dedicated for each and every channel is actually quite a, well, more feasible, I would say even an easier way to deal with this whole debacle. So that's where we're at. All right, so that's where the project is at. So after just doing a bit more revising with the knob, I think we're seeing the light at the end of the tunnel for at least something that resembles the first prototype. Of course, I'd have to do a bunch of testing with all these other MIDI messages, all the different MIDI applications. I personally would be perfectly content if all it does is forward the keyboard note on, note off, and maybe control change messages, and that's it. I wouldn't bother with like system messages and stuff, but you know, if I'm advertising this thing to look like a MIDI split board, people would probably expect it to support other MIDI stuff like program change stuff maybe. So we'll see how it goes. Hopefully we can get up and running, and that will hopefully finally be my first fully completed piece of musical hardware under the Dex and Winston brand. Alright, I'll see you guys in the next one.